So this was the first slide I made for this presentation. Living in the future, because I think we keep on feeling like we're living in the future, and hopefully trying to get the future to come even faster than that. And this whole presentation, instead of telling you about living in the future, I'm going to take you back to the past. So we are in this kind of realm, this kind of community where we're doing systems programming. But I've also been participating in a different kind of community for the past few years, and that is in binary exploitation. And binary exploitation is surprisingly fun. Unfortunately, most of the time it's like for evil, but I try to do for good. But these two communities have existed sort of in parallel for decades, and this presentation is sort of bringing that home, hopefully. So I'm going to have this kind of setup where I'm going to tell you like the past and the future, or current. So for boomers, 2000, that was Y2K. For the Zoomers, 2000, Taylor Swift was 11. Seriously, that's okay. So thank you for coming to my talk, Classic Vulnerabilities. My name is Patricia Aas. I'm a trainer and a consultant. I'm a C++ programmer. I've been programming in C++ since 2005, so 17 years now, almost a full adult. Working with application security and a lot in the area of C++ and C. I work for a company that I co-founded called TurtleSec, and I started my career working on browsers. I worked at Opera Software, working on the original Opera browser. Then I had a short stint trying to be a Java programmer, and then I went back to C++ at Cisco, where somebody reminded me yesterday that I was also working on browsers while I was at Cisco. And then I wanted to do browser full time again, so I went to Vivaldi. And for people who follow me on Twitter, I have like aspirations for doing more browser stuff. So I have a master's in computer science, and my pronouns are she, they. Okay, so why me? You know, why should I talk about these things? I currently do some teaching, so I'm teaching this introductory course to C++, and also now an intermediate course. But I've been teaching insecure C++ now for years. And I'm actually, and some of this presentation comes sort of from my work in creating the follow-up course to this, which I hope will be Hacking Doom. But let's go back to 2000. So for me, this period of time was kind of around here. So I finished my bachelor around here. It doesn't really make sense because you don't see the graph, but if you see the graph, that's where I finished my bachelor's degree. If you don't recognize the graph, this was peak.com. This is like if you knew one HTML tag, you got hired. I finished my bachelor there. I started my bachelor there. I got a master's degree. Okay, so you might remember 2000 from the music, right? So Destiny's Child came out with "Say My Name," which is an awesome song, by the way, and NSYNC came out with "Bye Bye Bye." It's a little bit darker than expected, but thankfully I had the titles. So for Zoomers again, this would be before Beyonce went solo. And I don't think Zoomers know who Justin Timberlake is, but he also went solo in the meantime. So in July of 2000, Solar Designer, which was the hacker name of Alexander Pesliak, presented what he called a generic heap exploitation technique. And so we're going to spend most of this keynote talking about this. So his idea was that if you could create some kind of portable exploit, and that exploit would be against the allocator, the system allocator. And he presents it around Douglas malloc, but the same type of exploit, or a sibling of it, has been used against many different implementations of malloc. And the idea was that if you could create something that worked against the malloc implementation, then you could use it against many different applications. Because even today, most exploitation is specialized on a specific application. So a security researcher will say that they are specialized in Acrobat Reader exploitation, or Google Chrome exploitation, or they will specialize within a certain application. So the idea here was, what if we have like these portable exploits and we can use them against many different applications? I don't think this actually worked out as well, but the technique itself became quite popular. So I have these slides where I have like links to like all sorts of things if you want to look more into these things. But I will post the slides later. I'll make a PDF and put it on Twitter, and then you can go and look at all of these things. It's often referred to as an unlinked vulnerability, and we'll look at how that can manifest. And so we're going to look at how it manifests in Chocolate Doom, and the reason for this. so again, for the Zoomers, this was like where old people learned first-person shooter games. The graphics were awesome, by the way. They were exactly as good as they look on the screen. And you could even network these. So you could, if you had a LAN, you could like play against each other, and it was really awesome. And I spent some of my misspent youth doing this. But Chocolate Doom is a source port of the original Doom game, which was open sourced in the early 2000s. So this is probably one of the more popular ones. So what happened was that, they did this, and then later on somebody made another kind of a friendly fork of this, which is called Crispy Doom. And then 3 years ago, Jason Taylor did a 10-hour Twitch stream, I think, trying to port the C game to C++. And then I got COVID. So having COVID, being like I did have a very short attention span. So I basically sat down and I just continued where Jason had left off. And it's still not done. Like porting something from C to C++, and especially a game from the 90s, it's been very interesting. But the plan is to try to use this in a future training. But in the preparation for this talk, I'd kind of decided which vulnerabilities I wanted to look at, and then I was hoping I could find them in Chocolate Doom. And I was positively surprised to find it. I guess that's a weird thing to say, but it makes it easy to explain. So in Doom, they have their own malloc. It's called zmalloc. There are 2 different implementations of it. We're going to look at the implementation that's called native. So this has some metadata in addition to the memory that it is allocating. And this metadata is mostly game related. So it has some stuff about if it is for a level, for example. So then you might want to clean up after the level is over and things like that. We're not going to go into like the features of this malloc. It's used all over the game. And in all sorts of auxiliary processes as well. So when you use it, it looks something like this. So here we have this floor move T, and then you just use it like malloc basically, except that you have some additional parameters. So here you have this tag thing and this user thing, and we're not really going to talk about either of those. That's why I want to point them out on the slide. So it basically means that the pointer that we're going to give to the caller is to this chunk of memory here. But in addition to that, before that, we have this mem_block T. And that's where our metadata is going to be. So these are going to be adjacent to each other on the heap. Okay, so let's have a look at mem_block T. And we're going to look at the implementation for Z native, which is the one that we're going to be looking at here. So again, a reminder, this is located right adjacent to the memory that we're going to return from malloc. And it looks like this. So here's the tag from the previous slide, and here's the user thing from the previous slide, and we don't care about either of those, but we care about these two. So these two are previous and next pointers because these things are linked in a doubly linked list. So that looks something like this. On the heap, so you have this allocated block, which points to the first one, and then that will point to the next one, and that will also point back to the previous one. So this is a classic normal doubly linked list. Where the nodes are adjacent to the memory that they are associated with. Okay, so when we free one of these pointers, we're going to pass this void star pointer to this function zFree. And the first thing that happens is we're going to try to get a pointer to the metadata section, and then we're going to do some checking. We don't really care about that, we care about this part here. So before we actually do the real free on line 19, we're going to remove the block. Okay, so this is remove block. This is like copy pasted directly from the code. Here on the slide it says, let's see if I can do that. So it says CPP, and that's because I'm just using my code from the CPP port, but it's the same in the C version. Yeah, so except of course I've changed all the nulls to null pointer in one of my 500 different commits that I did while I had COVID. Yeah, anyway, so it does some checking. If it's the first one, it's going to set the global pointer to it. If it isn't, then it's going to do this thing. Okay, so on line here, 7, it will just set that one to blocks next to unlink it from the list. And on the second one, it does, if this blocks is previous is next, I'll do it on the next slide. Okay, I'm gonna show you on the next slide. Basically, this is classic unlinking from a doubly linked list. Better with a picture. Okay, so let's do it with the picture. Let's see here. So we're gonna have a look at the bottom one first. And so we're looking at this pointer up here. And so this is blocks is next, previous. and we're gonna set it to blocks as previous. And then the same thing on the other side. So we're going to take this pointer and we're going to set it over there, and that unlinked this block from the list. And now you're free to free it, for example. No pun intended. Okay, so there are a couple of insights in this type of exploitation, but the most important insight here is that if we can control both sides of an allocation inside of the application, then we can control both where something is written and also what is written there. That is called in security researchers speak a write what where primitive. So I'll show you what that looks like. So this is remove block, now condensed a little bit for the slide. So the idea here is that if we can somehow control block previous, then we can control where the write happens and adjust it for the offset of next, and I'll show you that later. So this is where, right? On the other side, you have, if we can control block next, we can control what to write there. So then we have what? So now we have both sides of this equal sign. So if we can overwrite these two values, we can control both sides of this equal sign. And so when the unlink happens, whatever assignment we wanted to achieve will be done. So this is a write what where primitive. This is what it looks like. Now the idea in exploitation is that we're going to make some manipulations or somehow change things in memory, and later on when execution comes to this point naturally in normal program flow, instead of doing what it's supposed to do, it's going to do this thing that we wanted it to do. Okay, so I made a proof of concept and I gave it to the Chocolate Doom people, and I also made a patch, and it was merged a week or two ago. Yeah. So the idea is we're going to corrupt the metadata, and then we're going to free it, and then we're going to see that the write what where happened. So it's not very pretty. I'm just going to walk you through like the important bits. So here, this is the memory that we're going to free later on. I also did an allocation before and after because I wanted to have an actual list where it actually had a previous and a next. And here I'm just going to get a pointer to the metadata. This is the where. So this is where what we're going to use for our where side. And this is our what. Here where I'm going to try to adjust for the distance to the next pointer. So let's see if I can point with my clicky thing. Oh wow, okay, there we go. So basically I'm just saying to subtract the distance to next from the beginning of the header just to figure out how far away it is. And then I'm going to subtract that distance from the where pointer. And the reason for that is that later on, when someone does the next, it will just do the reverse. It will add this distance. So now I'm removing it so that the adding later will result in nothing. I'll show you again on a later slide. And then I set the previous and the next. So first here, I'm checking that where is still a null pointer. Then we do the free. Then I check afterwards that the where no longer is a null pointer, and then it actually is the value of the what, which was up here, which is 42, 42, 42, maybe another 42 in hex, which apparently hackers think is awesome. Okay, yes, so where has been set to what? So this is the basic proof of concept, but when you think about it, okay, Patricia wrote a C program or a C++ program, depending. Where she corrupted memory is not like super interesting, right? But first I want to show you the next thing. So if we have a look at what this means in memory, so the yellow box here is the block prev thing, except I have done the subtracting of the next offset to the where pointer. And here we have the what. So if we have a look at the bottom here, this prev arrow next will be block arrow prev plus the offset of next. And since we subtracted it already, it will just be nothing. So where will be equal to what? Okay. So before I talk about how this would be exploited in real life, the traditional mitigation is quite simple. It checks the pointers before it does the unlink. So here is a simplified version of the patch that I gave to Chocolate Doom. So the idea here is that we're going to check that the pointer actually points back to us. So here we're checking that blocks is previous is next is block. And if it isn't, then we do an exit. If it is, then we just move the pointer like we usually do. And then the same thing for the other pointer. Like that. And you will see various different versions of this and many different types of malloc that have implemented the same thing. Now, the weird thing is you'll think, okay, so why does this type of vulnerability exist in so many different implementations of malloc? And I've thought about this a lot because I teach this in my training, and I think that it is basically that the domain is very small. Like you have to implement malloc and you have to implement free, and then maybe some auxiliary more complicated versions of it. And you have the same problems. You don't want fragmentation. You want to have to reduce time for lookups and all sorts of things. And also many of them, of course, are implemented in C, where the linked list is the data structure. So I don't know, but it does happen in a lot of allocators that they use linked lists for different things. Oftentimes for free chunks. In this malloc implementation was the opposite. Okay, so how would you exploit this in real life? Like for this, you'd probably use a heap buffer overflow. So I would show you. So imagine again, this is our memblock T from before. So down here we have the object to be freed. Then we have our the fields of the memblock that are here. So this is for a 64-bit architecture where the size of int is 32, which is, in my opinion, normal. And and then up here we have the adjacent buffer object, whatever, where we're going to do the overflow from. So when we do the overflow will be overflowing the adjacent block, overflowing this metadata structure, and then we can overwrite the where and the what. And later on, when the object is freed, the unlinking will happen, which will cost the write what where primitive. How would you find these? Okay, so these are very hard to find in general without encode checks, because this is valid memory. Yeah, this is not like you're writing outside of bounds. This is memory that has been allocated. So when I run this with ASAN, the test case, okay, because I'm not like a real security researcher, I'm actually like a software engineer. When I write proof of concept exploit, I do it as a unit test in Catch 2. Then I put it in CI. and I make sure it passes on all the platforms, because that's what you do. But if this test case does fail with ASAN, but it doesn't fail for the reason that we would like. It fails. It fails on global buffer overflow on address blah 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 and remove block. And the problem here, I can probably show you. Maybe I can. It's not very big. Okay, but if you can see, it fails here. It fails later at when block next is used, which is not where our write what where primitive happened, which was here. So we had already succeeded at this point. So it's an aside. Then we did memory corruption, so it's fine. Yeah. So what do you do? There are hardening of allocators, and you can say adding such a check to the allocator is one type of hardening that you could do. But yeah, it's a problem. Yeah. So this is for the pull request and the proof of concept and the issue at Chocolate Doom. Okay. So but this was the past, right? So this was 2000, and now let's. I'm just gonna get my phone so I can see what time it is. There we go. But let's look at the future. Okay, so 19 years later, let's have a look. So we're gonna have a look at vulnerability in Android, which is nicknamed Bad Binder. So this was discovered being used in the wild. It was reported to Google, but it was reported as more of, we know that someone can do this. We don't exactly know what they're doing. This is their sales material. Try to figure it out. So this is CVE 2019. So for people who are not familiar, CVEs are basically a global bug reporting system for vulnerabilities. So they use the year as the first part, and then there's just an increasing number at the end. Yeah. So from the CVE, it says, use after free in binder.c that allows an elevation of privilege from an application to the Linux kernel. So for people who are not like super familiar with Android architecture, this will be like the fastest introduction to Android's IPC mechanism ever. Okay, so in Android you have this concept where you can do IPC between different processes, and the IPC is basically abstracted to a function call. So it looks like a local function call on your side in the application, but it will result in an IPC being performed. Oh, for people who are not familiar, IPC is inter-process communication. So imagine that you have some kind of caller and you have a callee, and then you want to do some kind of function call into the other process. Now, how this is implemented is using this kernel module, this binder driver, which for a long time was a patch on the Linux kernel, but I'm told it was merged a few years ago. So what happens, and what I think is kind of cool about this mechanism, is that when the caller makes the call, it actually does a system call down to the binder driver. The caller is swapped out, the callee is swapped in, the call is made, or the IPC thing is made, and then the reverse happens. So it will unwind back. So this will look like a synchronous call, and it is extremely fast, as opposed to many other IPC mechanisms which are asynchronous. And it's basically a context switch between the two applications that are communicating. This apparently was something that the idea was kind of stolen from Palm, who had a similar model, because a lot of the original Android developers came from there, as I understand it. Okay, so for our purposes here, there are two things that are important. So we have an application in user space that is making a call into kernel space, and then there's some stuff here. So I'm not going to go through it in too much detail. I have links to a talk that goes in more detail into it later, but I'll just give you the highlights. So the threat actor that was involved was something called the NSO group, and it was being reported as being used in the wild. For people who are not familiar with NSO Group, it is an Israeli technology firm. They make a product called Pegasus, which is evil, and it enables remote surveillance of smartphones, and they sell it to everybody. Or they'll probably say, no, we sell it to nations and law enforcement agencies, and I will say they sell it to everybody. Because the problem is, of course, that you sell this to some government that is oppressive, they will use it against activists, journalists, and that's exactly what happened. So Pegasus has been used for doing surveillance of journalists in all over the world. Activists, they have led to people being jailed and tortured and killed. So all around not a nice group of people, in my opinion. Anyway, so they had certain pieces of information that was available from the sales material that was being presented from NSO Group. And for this presentation, I'm just going to mention a couple. So one of the things was that they said that there was an arbitrary kernel read-write primitive. And for you here, write what where primitive can be used to create a read primitive or write primitive. And also another thing was that there was this property called config debug list that for some reason, if it was on, the primitive didn't work. And this one was specific enough to nail down the files involved, because this would only affect very few things inside a binder. Or inside of the Linux kernel, which included the binder. And one of the things that it turned on was this code over here. So if you notice here, this might look familiar to you. It's basically checking that previous is next is not equal to entry, or next is previous is not equal to entry. And if any of these things are true, then it's going to exit, right? So this is the traditional unlinking mitigation. So how it was exploited, in this case, it was exploited with the use after free instead of a heap of overflow. And it's quite complicated, and so I will refer you to the talk, I think plural talks on this. But I just want to show you how that could be used. So imagine again that we have some kind of heap. And here we have our previous pointer and our next pointer. And then at some point we do the deallocation, but of course the memory is still here. So as long as it's not allocated to anything else, if we do an access use after free of it, it might go okay. And we all know that that is one of the issues with the use after free. It sometimes works. But how it is exploited is basically instead that the attacker will make sure that they get allocated this memory. And then they will fill it with what they want to be there. And in this case here, you will put it in the where and the what on the previous and the next pointers. Later on, when the actual use after free happens, whatever is accessing this will then do your write what where primitive. And in this case, it was used to overwrite some data in the Linux kernel, making it possible to root the device and then install the malware on the Android phones. Yeah. And since the unlinking itself is done in privileged code, so this was done inside of the kernel, it became use after free, leading to an arbitrary kernel read-write primitive, and then used to install Pegasus on Android smartphones. So how would you find this kind of bug? Because now we're in use after freeze, and use after freeze we generally have some tooling to find. I would say the best way to find them is probably address sanitizer, but the problem with address sanitizer is that you have to actually trigger the bug for address sanitizer to tell you that it's there. And in this case, how it was, the bug had already been found. And that's also one of the things that was an interesting thing. The bug had been found using a fuzzer called syscaller, which basically just has a grammar on how it fuzzes, so it does different system calls in different orders and things like that. And it has found I think tens of thousands of bugs over time. So they've said it's the hardest working security researcher. But syscaller found this bug, and it was fixed in upstream Linux, but it was never marked as a security vulnerability. So it wasn't backported. It was also, because it wasn't marked as a security vulnerability, which is policy in Linux that a bug is a bug. It was also not backported to previous versions. And so in one way you can say this wasn't a 0-day because it was known and it was fixed upstream. But unfortunately, it wasn't because of the way the community works and how we handle vulnerabilities. It wasn't reported to the people who could make those decisions later. Now, static analysis, unfortunately, doesn't really work really well with use after free, and I was going to show you a different example. So this is also inside of the Doom code base. So this is a use after free that was reported that my tooling found, right? But I'll show you what it looks like, and it's not super impressive. So this code actually has more fun vulnerabilities that I'm not going to get into right now, but I'm hoping to do some fun stuff with it later. Anyway, so here we have this command, and we're going to, so imagine here it was filled with some stuff from using this URL. And here we are calling system with this command, and we get some kind of return value. Then we free the command, and then if the return value wasn't equal to 0, then we're going to do something with the command. And so the tooling basically says this is a possible use after free, or this is a use after free, I think. Let's see what the wording is. Local variable command may point to deallocated memory, client ID use of memory after it is freed. Now, there are two things that I think are interesting about this slide. This is a very typical, it fits nicely on a slide, so I like it. But it's a very typical case where the bug is in an error path. So very often you will see a lot of vulnerabilities in unintended paths in the code. So you're getting junk data or something bad happens and you end up in your error paths, and these are not as well tested as the rest of your code. So the density of vulnerabilities is very high in error paths. The other thing that is interesting to me here is that the only reason that the static analysis tool was able to find them was that because they were so close together. And I would say because they are so close together, this is very hard to exploit. So this kind of use after free isn't super interesting, in my opinion, but it is the only thing that I think like a static analysis tool is able to find. So then you come back to, you have to use address sanitizer, and you probably have to use address sanitizer with fuzzing to be able to find these, because you have to exercise error paths, you have to exercise like weird input. So I really recommend people to try to set that up for their code bases. I also have lots of links here if people want to look more into it. There's a great blog post on Bad Binder. There's a video also where Maddie Stone talks about how they found Bad Binder by basically investigating the data that they got, and when I say data here, I mean like the pieces of information that they got from the sales material and rumor mill to try to narrow down where the bug actually was. Yeah. Okay, so let's go to 2002, and I promise we will not go in increments of 2. But in 2002, we had a wonderful tech moment here, and for people who weren't there and didn't experience it in real life, this was the wonderful video dilemma with Nelly and Kelly Rowland, where she writes what appears to be a text message in a spreadsheet. And on this wonderful Nokia phone, back when we had like actual keyboards and stuff, this was an excellent phone. And yes, and then gets kind of angry, I guess, because he's not answering her text. So in 2002, Nelly was huge. It got his breakthrough, I think, most in Hot in Her, and then of course this wonderful song with Kelly Rowland. And Kelly Rowland was also in Destiny's Child, by the way, which is where Beyonce came from, like for the Zoomers again. 20 years ago. So in 20 years ago, in Frack magazine. So Frack magazine is a kind of hacker online zine, internet zine, where people would share articles on different exploitation techniques or different things. This goes all the way back to the 80s and the phone phreakers and things like that. So it has a long history. And still online, thankfully. And there was basically an introduction to how to exploit basic integer overflows. And even by this time, this was old news. Like this was kind of like an intro for like the beginners. So basic integer overflows within this culture was already kind of considered to be like newbie stuff in 2002. So let's have a look at that. So we have signed integer overflow and unsigned integer wraparound, where we are the only people who care about the distinction between these two things. So let's have a look at a typical scenario where these things can occur. So here we have this code down here. So let's look at it more graphically. So we have this first buffer which has a length, and then we have the second buffer which has a length, and then we have like this third buffer which also has a length. So buff. So the basic idea is to try to figure out, is it safe for us to copy first and second into buff? That's what we're trying to figure out. So we get something like this, which is nice and safe and everyone is happy. Unfortunately, of course, we do this by adding first length and second length. So let's see how that could go wrong. So we still have first being, nice and kind and small, like it's supposed to. But for second, we're going to have an attacker-controlled length. Now, this is very common security vulnerability, that an attacker has some kind of length or size that they can control, for example, in a header, in a buffer, or something that is being sent to a server that is trusted by the server. So this is also the bug that was in Heartbleed. It's in many different big vulnerabilities. This is the root cause. So you have some kind of attacker-controlled second length, and here we're going to set it to max int because these are, in this case, signed integers. And then we have our buffer like before. But since this is a signed integer overflow, then this might end up being a negative value. And modulo some kind of compiler optimizations, which might just take this whole thing away because depending. But anyway, so let's assume the result is negative. Then we end up with this problem here that we will enter this if, because first length plus second length is a negative number which is smaller than buff length. So we enter the if and we're going to do our copy, and then we're going to have buffer overflow. So let's look at a different scenario. In this case, we're going to be playing with unsigned integers just for fun. So here we have our first buffer and our second buffer. But now here we are using maxUint, right, for setting the second length. And so here we're going to have an unsigned integer wraparound. So the result of this is going to be a small number. And if you see here, the idea in this code here is that we have, instead of reusing an existing buffer, we're going to try to allocate a buffer that is big enough. And we're going to do that by, on line 1 here, we're going to say first and second length is equal to buffer length. So buffer length will be the sum of these two lengths. And then we're going to use that sum to allocate our buffer. And then we're going to copy into it. So this looks innocuous enough, right? The problem here comes from the fact that the second length has an attacker-controlled value, which is maxUint. And so when this addition happens on line 1, it will wrap around, bufflen will be too small, and we'll allocate a buffer that is too small, which looks like this. It's a baby buffer. And so later on, when the copy actually happens, we will have a buffer overflow. Okay, so this was a known technique. This is basically how integer overflows and unsigned integer wraparounds are used in exploitation. They're usually used in some way like this, by bypassing some kind of if checking, or causing a buffer to be allocated to be too small, and then causing some kind of a buffer overflow, often on the heap, especially these days. Okay, so let's go to 2017. Okay, Google Chrome. This is CVE 2017-15.416. From the CVE, Heap buffer overflow in Blob API in Google Chrome allowed remote attacker to potentially exploit heap corruption. So in this case, I'm just going to show you the patch, because I think that's enough for this. So this is the patch. And you might notice here, there is a very similar code So here we're going to, there. So we're going to add two numbers together, and then we're going to check if that is greater than total size. The fix is to use this Chrome API that they have internally. So they have this check add to check if it's safe to do the add. If it is safe, they're going to assign the result to nbyte, which is here on line 3. And then they're going to do the comparison. Yeah. So there's a bunch of different things on that one. Okay, so yeah, so we were in 2002. That's when this was already old news in the security community. And let's go to 2021. Here, a vulnerability hitting Apple iOS, iPad OS, and Mac OS in CV 2021-3860. From the CVE, an integer overflow was addressed. Processing a maliciously crafted PDF may lead to arbitrary code execution. And so I'm going to show you the code, but I'm going to highlight the things that you have to care about. So because it's a little bit too much. Okay, so here we have an unsigned integer, a 32-bit integer. Then we're going to increment this integer with attacker-controlled data. So imagine here that we are going to increment it maybe with, uint max or something like that. Then here, we're going to use that integer to control the size of what we're going to allocate. So if we have managed now to make it wrap around, this buffer will be too small. And then we are going to copy into it attacker control data. So this is an example of the second one where we are allocating a buffer that is too small, causing a buffer overflow. Yeah, lots of stuff to look at. I have so many of these though. So if you want to dig into them, I will put up the slides and then you can look into each one of them if you want to. So how would you find signed integer overflow? You can find signed integer overflow with UB sanitizer, but again, you have to actually trigger the overflow, which again means you probably have to run it with a fuzzer. I recommend in my trainings people use libfuzzer, which comes with Clang, which is excellent, really fast. And it's already integrated probably in your tooling. UB sanitizer, address sanitizer are available and many other sanitizers are available in Clang and GCC. Address sanitizer has been ported to most kernels today. So for example, for the Linux kernel, there's a KSAN. And for the BSD kernels, there are also address sanitizers for those. I'm sure Microsoft has ported one to their kernel, although I don't know that for sure. What I do know is that address sanitizer is turned on in Apple Clang as well, and as two years ago, this pandemic is messing with my time. Let's say 2 or 3 years ago, address sanitizer was also enabled in the Microsoft compiler, and as of last fall, I think it was also available for 64-bit. So basically, address sanitizer, you can run it in basically any modern compiler that you have accessible today. So you should try that. So with libfuzzer, it's integrated into Clang. So if you have a Clang build, you can use it there. There are also other fuzzers available. So UB sanitizer can find signed integer overflows. But for unsigned integer wraparounds, you have to use integer sanitizer because it's not UB. The problem, and I kind of brought that up before, is that for the purposes of exploitation, it doesn't really matter if one is UB and the other is not. For the purposes of exploitation, it just means that if I can control one of the numbers in this addition, then I can make the result of it be small. And if that small is negative or if that small is a small positive number, it doesn't really matter for the purposes of exploitation. In C++20, we get safe integer comparisons, or we have gotten for the people who are living in the future. How many people are actually using C++20 now? Okay, congratulations. I am not at all jealous. Okay, so this is example code from CPP reference, and so these are some things that we're getting in C++20. Hopefully there will be other things like this in the future. You also have things like std midpoint, which is also kind of addressing a typical scenario around adding two numbers together. Because this is one of the things that I find hard. It's like I'm teaching beginners in C++, and typically when people are starting to learn a new programming language, they start by writing hello world, which is not great in C++. And then the next part is they're going to read a number from the terminal or two, and then they're going to add them together and write out a number, which is probably like the worst part of C++. But it is what it is, right? So moving on. 2010. 2010, 12 years ago, Rihanna came out with Rude Boy, which is awesome. And Lady Gaga came out with Bad Romance because Poker Face was already a couple of years ago old. Wow. Time, I don't understand. Of course, this guy came out with this like really oversized phone that I don't think you could call with, or could you? You could call? You can make a call? Okay, so this is the original iPad, came out in 2010. Format string vulnerabilities. In 2010, in Frack magazine, came this wonderful post called A Eulogy for Format Strings. By this time, the security researchers have given up on format string vulnerabilities. In 2002, they had this advances in format string exploitation. By 2010, it was over. They consider this to be a field of nothing anymore. And of course, we're going to look at format string vulnerabilities. So I'm going to teach you a couple of lesser known format string features. So the first one is field width. Now this is like super useful if you're going to make like a terminal application and you want like a nice layout. So field width will basically just say, so here we're going to use the field width of 17. So we basically are setting a kind of a column width. So we want the field width of this entire field to be 17 characters, and then we're going to, in that field, write a number, which is 10 in this case. The nice thing here is that if you have used this, you can write things in nice columns and things, very, very useful. You can also use this % sign, and then you can read the field width also from the arguments to printf. You can even use a feature that I'm not going to get into here, which is called direct access, where you can actually select which one of the parameters you're going to use for field width. So this is, and this is basically, I wanted to show you field width, but I also wanted to show you that like format strings is like a programming language. Like it has so many features, it's ridiculous. Another thing that I want to point out here, which a lot of you know, but in code we sometimes forget, is that the first parameter to printf is a format string. So if you do printf variable endpren semicolon, you are passing that variable as a format string. If that variable is attacker controlled, they can do all of these things, right? Okay, next feature. Characters written. This is a weird one, but I guess it's useful for some people. So here we have a local variable num, which is a assigned integer, and we're going to do this printf here. So we printf a b c d e f and then %n, and then we're going to pass in as the argument the address of num. okay? Then later we're going to print out what num is. If we run this program, it will write A, B, C, D, E, F, and then it will write 6. Because this wonderful feature so a lot of you probably knew that with printf you could just you could print arbitrary pieces of memory, mostly from your registers or your stack or whatever, right? Most of you have done this because you added too many %ds to your format string and not enough parameters, at some point. And that is true. And even today, that is one use of format strings, to leak memory by just doing %ps and %ss and whatever, and trying to figure out what memory looks like. In this case here, we are writing to memory. So using a format string, we can write to memory. That's a little bit more unfortunate. More advanced versions of format string vulnerabilities will actually find the format string on the stack. So the string itself, which is somewhere, then it will take an address in the format string itself and use that as the address to write to. It's terrible. And I'm not saying that as like an exploit. No, I'm saying it as a programmer. It is the worst programming language you have ever seen. Trying to do exploitation in format strings is absolutely mind-bendingly awful, and I do not recommend. But of course, I'll show you a little bit how you can combine these two techniques. So one of the things that you can do here is we're going to use field width together with %n. Okay, so here when we run it, we're going to print the one like way over here, and then it's going to print 42. Of course, because field width was set to 42 up here, which means that it's going to say how far it got in num, which is 42. So here you can see that you can control the value that you write to this pointer inside of the format string as well. Okay. Anyway, there are much more fun things about format string vulnerabilities, but I thought those would be nice to show you before I bring you to, well, of course, okay, first of all, in 2002, we had advances in format string exploitation. By 2010, we had a eulogy for format string exploitation, and let's bring you to 2021. Apple iOS. So this thing, if I understand it correctly, it was just dropped on Twitter. So this is CV 2021-3800. And from the CV, joining a malicious Wi-Fi network may result in denial of service or arbitrary code execution. And when I show you the picture now, because I gave you like printf tutorial, you'll know what it is. So after joining my personal Wi-Fi with the SSID %p, %s, 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 %n, my iPhone permanently disabled its Wi-Fi functionality. Neither rebooting nor changing SSID fixes it. Yeah. And the thing is, it's a very simple mistake to make because you're getting some kind of value from the outside world. In this case, an SSID, right? And then you just want to printf that thing. So you do printf SSID, not realizing that the string that you're printing is user controlled, right? Which means it can actually include all of these wonderful characters. So this caused a cyclic crash of the entire Wi-Fi stack, I think, on the phones, and it became a problem. But they were able to recover. I don't remember. I think it needed to do a factory reset or something to get through it, and it was patched, of course. So how to find them? So the reason why there was a eulogy in 2010 for these is that not for address sanitizer, but for the format string warnings. We'd gotten over time more and more warnings about how to use format strings, and so a lot of applications had fixed this. But I think also that's probably one of the reasons why you will see it again in 2021, is that people weren't used to thinking about them anymore, right? So if you use address sanitizer, you would have found the %n, because it's basically writing to some kind of random pointer it found on the stack, right? Because if we go, let's go back. Let's go here. Because all we're controlling in the attack, we're just controlling this first parameter to printf. So if you have, what was it, %p, %s, blah, 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 %n, each %p will take something from, for example, a register, and printing it to something. We don't know because we can't even see. It's inside the phone, so it's probably a log somewhere. And then at a certain point, it will do the %n, and then it will just find at the appropriate location on the stack or in a register, it will just find a pointer, dereference it, and write something there. Now, this thing that it found and thought was a pointer probably is not a pointer. It's just probably just some random stuff. It's going to interpret as a pointer because that's how we do. And so it's going to write to some kind of random place in memory. So had you fuzzed this, you could have probably found it, but it's still, the problem with fuzzing is like you have to actually be fuzzing that specific interface. And that's also one thing that is kind of interesting. When it comes to, for example, Heartbleed, and I'm not going to go through that here because I've gone through it before in the past, but with Heartbleed was found by 2 independent teams at more or less the same time. And the reason why it was found is that both teams were working on making a fuzzer. And they wanted to test it. So it's like OpenSSL is right there. We're going to test our fuzzer on OpenSSL. Yeah. Fuzzing, you have to also fuzz the right thing, because the feature, for example, that they ended up fuzzing where they found Heartbleed was a feature that was basically nobody was using. So you also have to say, okay, I'm going to set this up as a test and I'm going to fuzz this thing that nobody actually cares about. And apparently, as far as I understand, was a student project that was merged into OpenSSL. Yes. So yeah, you can use address sanitizer, but again, you have to trigger the bug. And then make sure that you have all of your format string warnings on. If you are not building with any of these compilers, consider maybe to have a build with using these compilers to find them. But the most important thing is to look for, when you're looking for this, is there a format string, so the first parameter to one of these, is it attacker controlled? So is it something that someone outside of this application can change the value of? Oh, you want to take a picture? Okay, so let's go back to the present and try to think about what does all of this mean? Because I'm kind of balancing these 2 communities. And what I can see balancing these 2 communities is that there's not a lot of us in this intersection of systems programming and binary exploitation. The people who are doing binary exploitation are usually participating mostly in their own community. And so the research that they're presenting in that community. And the crossover communication is not as good as it should be. And what we saw with the format string vulnerabilities is that there was a lot of focus on it, like 12 years ago, 15 years ago, but then it was considered both by us and by them to be a solved problem. And then we forget, right? So I don't know how to fix this, and I guess maybe that's why I do this. I do these talks, is to remind us that there is a parallel community that is also learning together with us, and one of the things that I also teach in my training is is that they are using the same tools that we have available to us. They don't have any kind of magic sauce. And usually what they're working with is much harder than what we have to work with. So they're using address sanitizer or similar things. They're using libfuzzer. They're using our compilers. They're using our toolings. And we could do that too. Those tools are even easier for us to use than it is for them. So one of the things that I want us to do is to get better at using the tools that are available to us, and to realize that some of the bugs that seem silly, like assign integer overflow, which seems like who cares, to understand how that is used in exploitation, and also to understand that these ways of using them in exploitation are not, they're patterns. Just like we have programming patterns and design patterns, they have programming patterns and design patterns, and they name them things, right? So like the unlink vulnerability. The unlink vulnerability was presented as some kind of magic bullet for heap exploitation. But the one that was in Android was a different kind of list. It was just a list. It was just a linked list, but a linked list has an unlink. And so somebody looked at this, found a use after free, looked at the code and so go, ooh, oh, we have a next and a previous pointer. I know how to do this. Just like we do when we look at code and we go like, oh, I recognize this, this code or this kind of situation. I know how to solve this problem. They also do that. And so it's important to realize that they are not continuously making up things as they go along. They have a whole history and a whole lore and a whole body of work that they're building on. So we like to think that we're living in the future. But I'm starting to wonder if maybe we're just kind of like reliving the past. And somebody came to me and they were like, we were talking. I think it was in the office when I was talking about this, and somebody said that all of the stuff we had in 2000 was like basically like the stuff that we have now, except now they work. And the thing is, I think I remember having that conversation 10 years ago as well, where people would say all the stuff we have now are the same stuff we had in the 90s, except now they work. And for people who are too young to remember, like in the 90s, we would actually read the manual and still not be able to program the VCR. And I can't explain VCR to Zoomers, but we've tried to make Netflix in our own house, okay? With physical things that we exchanged with other people, and okay, it was a whole thing. But I think maybe also that thing, like I've gone to these conferences and I've talked about CVS, and then I go like, oh yeah, CVS is like Git for old people. And I think maybe there's some truth to this. Like we keep on reliving the past. You meet people and we're like, we have social media now. And then you meet somebody in their 40s and go like, I was on IRC in 2000. You can even do /me in Slack, right? So it's maybe we're not living in the future as much as we'd like. And maybe what we need to do is to start learning from each other and to communicate across communities. And maybe we should be better. Maybe more C++ people should go to security conferences and do talks there. And maybe more security people should come and do talks here. And having that, like security conferences would probably be super interested in like beginner talks in C++, because they are, when I talk to security researchers, they often tell me, oh, I'm a really bad C++ programmer. Because they do C++, but they do terrible C++ because they're just kind of making it up as they go along. So having some kind of cross-pollination would probably be a good idea. And I think that's the moral of this entire story, is that we might not be living in the future as much as we think, and we should talk more.
You mentioned format string vulnerabilities in the context of printf and similar kinds of functions. Now, in C++, 20 we get stood format. which has an entirely different approach and a reasonable amount of compile time safety. Can you comment on std format and future format string vulnerabilities?
Well, as far as I understand, I've been playing around with it a little bit. Most of these are not possible to do with FMT at least, which is what I've been playing with. Which I joke with Victor on Twitter sometimes. You know, when he says, "We need, like, what kind of features do you want in FMT?" And I'm like, format string vulnerabilities. But hopefully we'll get better. Yes. The problem is, of course, that anyone can printf at any time.
Are there things beside fuzzing, sanitizer, and testing which developers can do to keep their code safe?
So the problem is that we are working within an area that has, you know, it has a lot of foot guns. There are lots of ways to make things blow up in various ways. One of the things that I try to teach in my trainings is, for example, for people to go to more value-oriented programming, more modern C++, not newing everything all the time, being careful around pointers. But all sorts of like higher level things will have a lot of safety built in. But I think using the tooling that you have, there's IDEs with built-in Clang tidy, which will give you like inline warnings about things and fix-ups. But I've also come to the conclusion that programming is a social activity. We do it with other people and we learn from other people. And so getting feedback on your code in a way that is not mean, like people will tell you like, oh no, this is not how we do things. But yeah, the tooling has gotten better. Like the tooling is much better now than it was. So use the tools available, I guess.
How much is this a C++ problem, and how much is this affected other programming languages?
Okay, so was it yesterday? Time again. I asked on Twitter because I got this kind of question the other day as well. And so I asked, can you have heap buffer overflows in Rust on Twitter? And apparently, yes, you can. Yes, you can, except they try not to, which I guess we do too, so that's fine. They also have a lot of the same tooling, by the way. So they have ASAN for Rust as well, and the same fuzzers as well. So yes, you can have these problems in most languages. At some point, no matter how high level you are, you're going to hit a low level API, and especially if you're going to receive data from over the network, if you're going to receive or read data from disk or so yes, you can. I think probably you will get it more in more C-like handling of memory, or raw pointers. I think using libraries more, and basically that's what the Rust people said. Yeah, but we don't do this. We use these containers, and then we're like, yeah, we can also use the containers. Doesn't mean that we can't make this bug. So yeah, no, I think most languages can at some point have this. Like the Java developers in my company, you know, they love it when they get a segmentation fault in their VMs.
Hello. You mentioned about having better communication between the two communities.
Yeah.
But how does that square with the fact that, well, my reading of it is to say the binary exploitation community are trying to sort of subvert the systems programming world. What do you see as the result of that better communication?
Okay, so one of the things that I really like about the binary exploitation / hacker communities is this idea of being curious and learning, and they are looking at the interfaces of. So another thing I do talk a lot on Twitter. That's how I talk to people. But the other day it's we make abstractions and then we pretend the abstraction is complete, but all of our abstractions are leaky, and we make layers of abstractions, and hackers often look at the abstractions and trying to figure out where they fail, and that is a learning activity. It's not an attacker activity, it's a curiosity, and I think that we would learn a lot from each other, and I think a lot of that we could integrate into our own work. Yeah.
Hello, thank you very much for being here, being part of that that process. So you've done your bit. So my question, you may not have an answer for it, and it's not your responsibility to do that, but have you got any suggestions about how we get that into community? How do we get people attending each other's conferences, and how do we get them accepted at those conferences when they present something that's out of the usual for it?
Yeah. No, I think, and I think maybe it goes to what we all kind of do when we submit talks to conferences. We kind of have to figure out who the audience is and where they are in their learning and skill level. And one of the things that I think you will find, in especially the conferences that are dealing with binary exploitation, is that they are very much interested in many of the same things that you are, and they're looking at the same types of tools that you are, but maybe in like from a different direction. But one of the things that they often don't have a lot of is formal or rigorous education in the programming side of things. And that's where I think that we could participate more in the introductory stages of teaching C, C++, modern C++, also maybe compilers, compiler internals, things like that, I think are definitely things that they would be very interested in.